Hey, my name is Tanveer, and today we are going to look at the essentials of setting up and monitoring the distributed training job. I'm not going to discuss the infrastructure aspects in this video. Okay, so I'm not going to tell you like how to set up the multi-node cluster, how to establish a communication between the various GPUs, but we'll focus on like if you have that thing done, how to set up a distributed training job. Okay, you can take a lot of projects from the GitHub which has the distributed training jobs. So you can choose one of them and you can try running it out to learn it more. If you have any questions about the infrastructure, you can look at the previous video. So as I said, like the prerequisite for this video is you need to have this multi-node, multi-GPU clusters. It could be on a cloud, it could be on prem. Then you need to build your environment. You need to install and set up the environment with the essential things like CUDA so that the GPUs are able to work. The GDR copy, which basically helps in RDMA, which is remote directory management access. The GDR copy enables enables the GPU to copy the data from another GPU without involving the CPU and the RAM, which basically reduces an additional copy of the data, which basically in turn reduces the latency. So with the help of GDR copy, one GPU can copy the data to another GPU without even involving the CPU and the RAM. The third thing is NCCL, which is NVIDIA Collective Communication Library, which basically consists of like the collective communication premises into a distributed world or a distributed world of a GPU. EFA is an elastic fabric adapter, which basically talks with the NVIDIA Fabric Manager, and it's kind of an network interface which is written so that NCCL can talk to the AWS infrastructure for the network communication. Then you would need things like CUDA compiler so that the CUDA code can be compiled and is translated to a form in which the GPU can execute it. Then you need an AWS EFA, which basically is a plugin for using this NCCL and EFA in the AWS environment. If you have any questions, I have a pretty comprehensive videos. You need to look at the previous videos. There are two videos, okay, which talks about it. So if you want to build this setup, you need to go and check on those videos. So at the time of starting, I'm going to talk about the setup that I have it, okay, and so that you will have a brief, you'll have an idea that what is an infrastructure that I'm going to use, at least for this one. So I have two machines. This is my machine 1, this is my machine 2, okay. This has like 8 GPUs, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. So we have two machines, okay. There are like 8 GPUs here, 8 GPUs here, and we have already established the comm between these two machines, okay. As I described it earlier. So the machine that I have it is on AWS, okay. The machine name is P24 DX20X large, okay. There is on one machine there are 8 GPUs, which is A100. Each GPU has 40 gigs of memory, okay. So total two machines, 16 GPUs, and 40 into 8, which is 600, and 8 fours are 30. 40 into 8 in 8 times 8, 8 times 2, sorry. 40 into 8 is 360 times 640. So this is a total memory that I have it, okay. So this is how my setup is gonna look like, and we are gonna use this setup to run a distributed training job. Forgive me for the mistakes in the writings. So the first thing is to verify the setup. Okay, I've covered it in the earlier video when I was building it, but let's assume like somebody has built that setup for you, but before starting the training it will be a good idea to verify it out. So I'm gonna show you like my setup, okay, and how we are gonna verify it. So we'll verify it using a couple of ways. One is an open MPI, which is an open message passing interface, which basically allows us to run the processes in distributed manner on all GPUs, on all machines. The second thing is a simple Python script, okay, which uses torch, okay, to verify the GPUs. And the third thing is we'll run the job itself. We'll run the job itself, okay. So this is our setup. So we are going to verify this setup into these three ways, using an open MPI, okay, so using this simple Python script, and we'll run the job itself. So let's go back to the code, okay, and see how does this things looks like. Okay, so let's go to the setup, okay, that I have it. So I have two machines. Okay, this is the first machine, 172, 31, 15 and 13, and the second machine is 172, 31, 11 and 213. I have the setup in the Docker, okay, so I'm gonna just get into the Docker. The first thing that I'm gonna test it out is to ensure the SSH is working between these two machines or not, because if the SSH doesn't work, nothing is gonna work. So 172, 13, 11, 213. There you go. I am able to do an SSH. I'll go to the second machine, 172, 31, 15 and 13. There you go. So SSH seems to be working. I am able to get onto both the machines. So that's like a very important thing. I just need to check it out whether the audio is working, because I screwed it a couple of times. And I'm gonna get into this library nccl test, okay, to run the test. I have already installed this library. The installation instructions are there in my previous videos, so you can go and check it out how to install this nccl test. Before that, I'm going to like export couple of paths, okay. So the first path that I'm going to export is this, the second path. So I'm putting whatever I installed onto the path so that it's accessible to the system. So I'm onto this nccl test, okay, and I'm gonna run this nccl test. And the nccl test, the way we are gonna execute is using something called as an open MPI. Open MPI is called as an open message passing interface, which is like a fundamental backbone for a bunch of like distributed system, and it has been around for a while. So what we are gonna do is we are gonna use an open MPI, launch processes on all the 16 GPUs that we have it, and see if we are able to like launch the processor on all the 16 GPUs from each machine. Each machine has an 8 GPUs. So in order to like, if the communication is established, we should be able to launch the processes on all the 16 GPUs. So I'm going to walk you through the command as well briefly. Okay, so I'm going to walk you through with the command for testing nccl using message passing interface, which is MPI. So this is a command, okay, this is basically a launcher for MPI. So we are going to launch it from OPT Amazon Open MPI that we installed it in my first and the second video. This first parameter of this thing is ---- host file, and which basically contains of files, and I'm going to show you the files. So this is the host file. It has the two parameters. The first parameter is a private IP address, and the second parameter is the number of GPUs. You might have guessed that these are the private IP addresses of the machines that are part of my multi-node setup. Since I have two machines, okay, so there are two entries in there. So I have to put the IP address of the machine itself. Okay, so this 13 is my first machine and 213 is my second machine. So and they both have an 8 GPU, so that's the reason my slots are 8 and slots are 8. I have kept it on the same thing over here as well. So here it's the same entries, like 13 is the first machine and 213 is the second machine with the 8 GPU each. I just close the file without making any changes. The second part is EFA use device RDMA. So this basically enables a flag which asks the OpenMPI to use an elastic fabric adapter, which basically can turn on this remote directory management access of the GDR copy, which basically helps us in copying the data from one GPU to GPU directly without involving the CPU and the RAM. What happens traditionally is when you copy the data from one GPU to another GPU, the data gets first copied it to the CPU, first copied it to the main memory using the CPU, and then the CPU got involved and it copies the data from the main memory to the second GPU. So it adds a latency because there is an additional hop for the data, and it increases the memory usage as well. So GDR copy avoids that. And to make sure we can use that in an AWS environment, we need to keep these flags on. LD directory path is basically setting up the path for the various libraries for NCL, EFA, CUDA. Okay, official adopter of AWS adopters of an NCCL. Okay, then there is a flag, this NCCL debug info. It's for the logging level. Okay, so I want to print down the logs up to the info level. So info is the most detailed logs, right? If you want a lesser logs, you can use either warning or an error. This map by is a command which basically deals with the resource allocation and the mapping. And here I'm specifying 8. So it tells basically it instructs the MPI to launch 8 processes on one node. Okay, per node. See, I have 2 nodes, so 8 processes will be launched on one node. So in all, I'm gonna launch 8 plus 8, 16 processes. So here you can control the number of processes that you want to launch, and n minus 16 is basically 8 times 2 because I have the 2 machines. And since I have 8 GPUs, I'm gonna make sure that each process will be launched on a one GPU. This minus MCA PML is point to point management layer for communication. And it basically excludes the protocol. So there is a negation over here, hat CM. It basically excludes some protocol called CM, and it will just use a protocol called OB1, which is optimized for point-to-point communication with EFA. This parameter MCA BTL is a byte transport layer. So we want NCCL to use a TCP protocol for the byte transfers for machine-to-machine communication, and for the self and a different protocol when the machine is going to communicate with itself, or the GPU within a machine are going to communicate. Okay, this MCA BTL TCP if exclude and allow Docker. This is for some sort of a loopback of the network interfaces for the Docker container. It ensures the MPI doesn't use the loopback interface or the Docker virtual network for the communication. Okay, bind to none means we are not binding any specific process to any specific GPU or a CPU core. We are letting MPI to basically decide whatever process they want to launch on whatever machine, on whatever GPU. So we are not binding it here. If you want, you can do it there. This all reduce performance is basically an operator which tests the performance or the benchmark tool for the all reduce operation. So reduce is a very famous operation in the distributed world. If you had worked on things like a Spark or a Hadoop, you might have read about the distributed processing has 2 phases. One is a map phase and another is a reduce phase. In map phase, all the parallel task operates, and they operate on a slice of the data which they used to get. And on a reduce function, whatever the results of those maps have to report it back. Okay, basically reduce collate the outputs of all the map tasks and create a consolidated output. So in the context of this distributed training, there will be a lot of things that will go as a part of the reduce operation, which is like a gradient accumulation, gradient synchronization, gradient accumulation. So each GPU will calculate the gradient on the piece of the data that they are working on it, and they'll send the gradient back, okay, so that the gradient can be averaged, and then the average gradient or an updated gradient can be published to all the workers or all the GPUs over there. So that's an all reduce preparation operation. B minus 8 is basically it says like the buffer size is like 8 bytes or a 8 bytes. The maximum size of the buffer is like 1G. Minus F2 is like how many times we want to double the load while testing the process. This minus G1 is an important parameter, and which tells like we need to run exactly one process on one GPU. Since we have 8 GPUs, so one process will run on each GPU on one machine, and we have 2 nodes, so we'll be launching 16 processes, and all those 16 processes will run on all the 16 GPUs individually. And n minus 20 is basically we want to that each test should run for 100 iterations for each buffer size. Okay, so we are gonna run it for 20 iterations, not 100 iterations here. Okay, and it yeah, so that's the command, and I'm gonna initiate that command on the machine. Okay, I'm gonna run it on both the machines, okay, so that we can verify it either way. Okay, so this is the first machine. I'm gonna trigger it, okay, for the 20 iterations, and there you go. You are seeing this message using devices. It's a good sign. Okay, and here you can see the output. Let me just extend it a bit. So here we can see on this machine on 13, I can see all the 16 GPUs, right? It basically had an 8 GPUs, but we got an 8 GPU from the neighboring machine, which is 213. Okay, and here we can see the name of the GPU, which basically contains the memory as well. And this rank is basically an identifier, okay, for identifying a GPU in a machine or in a cluster. So basically for the machine on which we are looking at it, rank will start from 0, okay, and it will go and it will increment by one as an additional GPU is added. So all these ranks 7 is still the machine which is 13, and from 8 to 15 we have the next 8 GPUs from this 213. Okay, because these are from the neighboring machine, so we'll exhaust all the ranks on this machine first, and then we'll look at this machine. If I go down, okay, I'll see the different initializations as well. Okay, we can see that initializing this AWS official NCCL, which is an AWS adapter for an NCCL. libfabric is another network optimization. CUDA is also there. Then we have EFA. We are setting a provider filter to EFA that will allows the test or the NCCL to use an elastic fabric adapter, which we want to use it in an AWS environment. So all those things seems to be initializing properly. And this is a topology file. We'll see like the topology file. So it basically defines how your machines are basically connected, how your machines are, what kind of PCI buses they have it, what kind of GPU had it. So it defines the network topology. And okay, here you could see that providers are EFA. So it seems to be like correct, and we'll see at the end of the test. Okay, the value seems to be okay, and these are like bunch of matrices which you can see for the performance. Okay, this itself will require a lot of time, so I'm not going to discuss in the detail. This is an amount of volume, so we are increasing the volume by 2 for each factor, and here you'll see like the time and all. I'll go to the another machine, and here we'll see the ranks. Okay, so for the GPU which we were seeing it as a rank 7, on this display it will be rank 0. As I said, like rank will start 0 for the host machine for one of the GPU, then it will get added by 1 as we keep on adding the GPU on the same machine. So on 213 it will be up to rank 0 to rank 7, and on 13 it will be rank 8 to rank 15. Okay, and here as well we'll go back and we'll see. Okay, the tests are done fine. So I'm gonna clear that thing up. Okay, and then we'll see a basic script like can we see we can access this thing via MPI, all the GPUs. I just want to make sure that we can access it using the torch, okay, because that's the framework that we are gonna use it. Training instruct lab src instruct lab slash training. Okay, I'm gonna go there. Okay, so cd. Okay, so I'm going to walk you through with the script first, okay, and then we'll look at the other things. So this is a very basic Python script. Okay, where is it is? Okay, check distributed. So I'm going to initialize the backend, which will be an NCCL. Okay, I'm going to get the rank of the various GPUs. I'm going to compute the world size. Okay, and for rank world size, I'm going to print out like how many GPUs are available. Okay, and then I'm gonna print it like all the devices and their names. Okay, print wall size. I'm a fan of this notation of using string formatter. Okay, so I have put it here. I'm gonna put the same thing on the slave machine as well. Come on, this is my slave. Run check distributed. This is something that I don't want. This is I'm gonna update it. Okay, so I'm gonna run a shell script. Okay, so we would need to set few variables. Okay, this master address, addressing port, the world size and all. I'm going to discuss about this variable little later, okay, when we are going to do an actual training, but for now I'll just submit it. Okay, so ls minus lrt, okay, and run training job, run distributed training setup dot slash this, control A. Okay, it's gonna take few seconds to run. Okay, so we can see like there is a rank of 16, right? Or I'm sorry, there are 16 GPUs available. Okay, and the world size is like 16, and there are 8 ranks on each. So here you'll see the ranks from 0 to 7 on this machine. Okay, here you would see like 0 up to 7 rank, GPU 4, GPU 5, GPU 6, GPU 7. Okay, and here you'll see up to rank 15. Somewhere you'll see rank 14. Okay, there will be rank 15 as well. So that you have seen it. So now we'll go and proceed to an actual training thing. So for the training, okay, we need to set up some basic hygiene. Okay, so I'm gonna change to my scratchpad. Okay, so setting up a training job. Okay, so the first thing is like verifying the setup. Verify the setup. Well, that thing we have already done, so we are green here. Okay, the second thing is, oh shoot, second thing is you need to put the code on both the machines. Okay, so basically we have this machine and we have this machine. Okay, and we need to put the code on both the machines. So the code has to be there on the both the machines at the same location. Okay, the third thing is you need to copy the data at same location on both the machines. So basically what we want to say is we need to replicate the setup on both the machines. Okay, so I have this machine, and here I put the code. Okay, and we all know like we can't train a model without the data, so we need to put the data. This is M1 and this is M2, so we need to put the data, and we need to put the data on the same location. Okay, because the data will be available locally to each machine. Okay, so and it will be faster, like the data access from here to here will be faster. These two machines are anyways gonna communicate, the com is there, but if they have the data access locally, it will basically reduce the latency. There are ways, like we can put the data like here on some distributed file system like HDFS or S3 or some NFS, and we can let them read from here. Okay, but this is something that we don't want, because it will because this thing will add network IO. Sorry, so this thing will add network IO. Okay, will hurt the bandwidth, training will be slower, and latency will increase. So the ideal thing is to put the data locally on each of the machine for the reduced latency. The third thing, or the fourth thing, okay, it's the fourth thing. So this is very important. IMP, just make it. The fourth thing is you need to select one machine as a master. You need to select one machine as master. So right now I have two nodes. So I have one machine as master, and let's say, and my another machine is like slave. In my setup, I'm selecting .13 as a master and .213 as slave. So how I designate the master is a machine with rank 0, and this will be machine with rank 1. So what will happen? What happens is, like, if we want to add another machine, okay, we'll have it like this. Rank 0, this is M2. Okay, this is M3, this is rank 1. Then we'll have another machine which will have rank 2, M4. So as we keep on adding the machines, right, as we keep on adding the slaves, will increment rank by 1. Will increment the rank by 1. So this rank, okay, this machine rank is different than the rank of GPUs. Okay, so the ranking will happen like machine rank 0 for machine is like the master node. Okay, and it will have the GPUs, okay, with rank 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. This is all the ranks. Okay, and then we'll have another machine. Okay, it will have the rank sorry, 8. We have the 8 GPUs. Okay, so it will have like, oh come on, it is 8, 9, 10, 11, 12, 13, 14, 15, and these are the GPU ranks. So we just need to like make a distinction between what is a machine rank and what is the GPU rank. The third thing we need to do, or sorry, the fifth thing, we need to trigger the, come on, you need to trigger the training on both machines at the same time. This is important, okay? Otherwise the training will not process. So whatever slaves that you have added, you have to trigger. And since we have replicated the setup, okay, you have to go to the same file, same folders, okay, and you have to run the thing. The sixth thing is train model weights or checkpoint weights will be available on machine with rank 0. So you won't be finding the checkpoint weights on a slaves. So if this is my rank 0 machine, okay, it will contain the weights. Okay, this won't contain the weights. Rank 1. Okay, too bad. But the weights of the initial model need to be applied on both the machines. Okay, weight of initial model need to be placed on each of the machine that you need to train. That initial model that you need to train. Okay, that's important. So basically what we need to do is we need to have this machine, okay, replicate onto slaves. So rank 0 should be replicated on all the ranks. Okay, we need to make sure same code is there, same folder structure is there, okay, initial model weights has same initial model weights needs to be there at same location. Okay, so that's something which is important. Then you need to trigger the training on both, and train weights will be there on rank 0. So these are like the only or the most fundamental things about the distributed training. So let's go back to the code, okay, and I'll give you a walkthrough. and then we'll train the model. So this is my script, okay, and I'm on a slave, so let me go to the master first. This is the master thing, okay. So I have like a training job which basically is a shell script, and then I have a code. Okay, just 1 minute. Okay, so we have both these things. So I'm gonna I have a shell script and a training job. So these are the environment variables that you would need to set, and these are the environment variables that I have set it up in my other script too. So this is a master address. So this is an address or IP address or a private IP address of the machine which has the rank 0. This is a port number. Okay, so all those machines, okay, which are on the network or which are into our multi-node cluster. Okay, so sorry for an interruption. So this master node is the address of the machine, or the private IP address of the machine which has the rank 0. So whatever machines are there in my cluster, okay, they are gonna communicate, okay, and they are gonna communicate to a port. So I'm giving this port number, and the port number has to be same between the masters and all the slaves. The world size is the number of machines that we have it, not the number of GPUs, but the number of GPU nodes that you are using. So in my case, I'm using the 2 machines, so it will be a world size of 2. The topology file is basically contains the network topology of your multi-node cluster. It comprises like the kind of GPUs that you have it on the nodes, the kind of CPUs that you have it, okay, and what you have it, and the kind of PCI or the serial buses, and all things related to the network topology. These are the Hugging Face parameters, so I'm gonna skip it out. This TB is split data on QPS. So there is something called as a query pairs, okay, and which basically what we are telling here is not to use the query pairs, okay, QPS equal to 0. So it basically it's basically we are stopping the NCCL to data to split the data across the multiple query pairs. This could lead to like limit the performance in certain conditions, but it will simplify a lot of stuff. So all the machines in the NCCL algo, so all the machines has to be connected with certain sort of a topology. If you have studied computer networks, there are like various ways of the topology. The ring is like one of the simple way, and we are using an NCCL algo as ring. Okay. And this will be used for like collective operations like all pref, okay, in the distributed system. This NCCL debug subsystem, so this tells us like what all NCCL subsystems we want to enable the logging. And here we are using this 4 systems. Init is for the initialization of NCCL context. The graph is basically they creates a communication graph or a communication topology. So there will be a information related to that as well. Environment is about parsing the environment variables and how they are impacting the NCCL. The logs will be around that. And tuning, like certain sort of a performance tuning decision which the NCCL has made. This NCCL debug equal to 1, it's basically the logging level. I'm using a logging level of warning. If you want a more deliberate logs, or if you want more extended logs, you can use the info. This OMP number of thresholds is basically open multiprocessing number of thresholds which is required for a parallel processing. And I'm using 16 over here to allow up to like 16 threads for an OpenMP task. It's relevant if you are running a operation that involves both CPUs and GPUs, like some data pre-processing on the CPU versus some other work on a GPU or certain type of communications. Okay. Ideally, this should match the number of like physical or logical cores available on your CPU for a CPU heavy task. Okay, and it can help in balancing CPU utilization with the GPU workloads. Export CUDA visible devices. So here I'm mentioning the GPUs that I want to use. So I'm gonna use all the 8 GPUs. So I'm had indexed it with like 0, 1, 2, 3, 4, 5, 6, 7. Okay, let's say in a certain configuration I want to use only 12 GPUs out of 16 for the training. So here, and maybe like 4 GPUs from this machine and 8 GPUs from the another machine. So there I can, here I can restrict it like 0, 1, 2 and 3, okay, to use it, and use 4, 5, 6, 7 for an inferencing. And on the other machine I can use it from 0 to all the 7s, 0 to 8, all the 8. So 8 plus 4 I can use the 12. So this you can basically use it to indicate like how many GPUs that you want to use it. The device max connection, it basically tells, okay, how many active connections of the GPU that you want to maintain. This you can tune it out for simplicity, for like performance easy, we just want to keep it one, okay, to keep the communication pattern simple. Okay, but yeah, if you are facing a throughput issues, then you can play around this number. Rank equal to 0 basically indicates the rank of your machine, and this, since this is a master machine, I'm gonna indicate the rank equal to 0. Okay, for the slave the rank will become 1. I'll show you the configuration file for the slave. And this is a torch run, so the training that I'm gonna run is using a deep speed, and the torch run will basically execute a distributed training job. Okay, and we are going to use deep speed along with a PyTorch, and a training form called as 0, which is 0 redundancy. Okay, and the data parallel training. So here we are setting the number of nodes, which is my world size, like these are number of GPU nodes that we are going to use, which is 2. The node rank, since this script will gonna run on a master node, so the rank will be 0. Nproc per node is basically 8, which basically tells the number of GPUs your machine has. The rendezvous ID is basically a unique identifier for the training job. There is a one identifier for each job. If you want to run the multiple jobs, you need to keep on changing the rendezvous ID, and it's a rendezvous ID with which they does all the collation of the results and keep tracks of the various things which is happening in the parallel. The rendezvous endpoint is basically where the end results or those things are get accumulated. I'm using this master machine and the master port that I had specified as a rendezvous endpoint. You can use your own key value stores for a rendezvous endpoint, and you can put it over here as a part of the endpoints. Okay, this model name is the model which you want to train. This is the data. Okay, this are like I want to do a checkpoint at the epoch. Okay, the learning rate, number of epochs I want to run it, say for 2 epochs. Okay, then LoRa rank equal to 0. I don't want to run it for I want to disable the LoRa, so I want to do a like full parameter fine tuning. So this is my script for the master node, and I'm going to show you the script for the slave node. Okay, so here I am not here. Okay, here I am on the slave nodes. So for the slave nodes, the only difference is in the rank. So rank is equal to 1. Okay, and the address of the master address is the address of my master machine. So this entire thing is like common between both the machines. Okay, the only difference is the rank part. And training, we are going to use a training by the deep speed. Okay, so I'm going to submit the job. Before that, I'll just disable the logging on the console. Sorry, logging on. So my logs basically goes to a file, and I'm going to stop it so that I can show you here. Okay, so I'm going to disable this 2 lines, okay, in my code so that my logs are printed. And I opened a side-by-side view of the training so that we can see like how the logs are coming up, and the trainings will be in sync. Okay, so I'm gonna run the training job. Okay, so there you go, and let's wait it to start it here. Okay, so this is gonna wait until unless I gonna trigger the training on the other machines as well, because I'm using a world size of 2. Okay, so slash ls minus lrt run training job, sorry, run clear. So this is not gonna proceed, okay, until unless I'm gonna submit that run training jobs.sh. Okay, so I submitted that part as well, and let's see. Okay, so this is some custom instruction that I put in. Okay, and there you go, the training has started. So you'll see like the logs on both the machines, okay, in parallel, and if it's happening in the sync, right, then your things are good. Okay, here you'll see the number of GPUs are like 16. So I'm gonna I'm using like both the GPUs on both the machines. Okay, and this number of GPUs are 16. We are gonna see how the loss is gonna get minimized for each of the machine. Okay, the wall size is 16. Okay, because we are using the 16 GPUs, and you'll see it in a sync manner, and I thought like to put it side by side so that they are visible better. What I'm gonna do, okay, here you'll see. See, here you'll see, okay, epoch 0, step 2, okay, it ran away. Okay, rank 7, this is a loss for the 8th GPU on the first machine. This is a loss for the first GPU on the first machine or the master machine. This is the log for the 6th GPU on the first machine. Okay, and this is the log for the 5th GPU on the second machine, the 4th GPU on the second machine. So you'll see like the logs, the loss will like, since we are training the model on each GPU with its own slice of the data, so we are gonna see the loss per GPU. Okay, and this is where it is. Okay, I'm gonna pull that thing as well if I can. Okay, so I'll just run the NVIDIA SMI in the loop. Okay, you'll see I'm using a bunch of GPU memory. Okay, right now I'll just run one more window. NVIDIA SMI minus L. See here as well. Okay, I'm using a good amount of memory on all the 16 machines. Okay, on all the 16 GPUs, I'm sorry, not the 16 machines. So you'll see the rank values as well. Okay, see rank 6, step 10. Okay, the loss is this much. Then you'll see rank step 10, rank 13, the loss is this much. So you're gonna see like rank by rank loss. Okay, and here we would see the GPU usage as well. Okay, this is the master, this is this GPU on the slave. So in this video, like I'm not talking about the strategies for like how to train the deep learning model. I'm gonna record a different video to discuss those things, but at least this video will give you an idea like how this distributed training proceeds and what are the things which you need to do to make it work, and what are the things to look for. So we are towards the end of the training. Okay, I just trained it for like 2 epochs. Okay, step 10 is there, and okay, here you can see, okay, here on the master machine you are seeing, okay, that my model is being, or my trained model is being saved, but you won't see anything over here because my model or the trained weights will be available on this machine but not on this machine. Okay, once the model is trained, we'll find the weights from here. If you restart the training, it will start from the latest checkpoint, okay, and it will resume it. So once the model weights are written, we'll be done. Okay, so it's about there. Okay, model is saved. This is the number of epochs. And we can see like the loss has been reduced, the per token loss scaled by the world size. Okay, I'm gonna explain the logs in some other video as well. Okay, and here's you'll see a bunch of messages. The point is like you'll see the logs into a very synced manner. If it's not syncing up, then there is something wrong. You have to replicate the exact same setup as well. So it's gonna end it. Okay, it will take some time to end it. It's on the 13th, right? So I'm gonna check at the weights. Okay, here you can see these are like my model weights. Okay, these are the date. You can see like 340. So these are the weights that have been written. Okay, if I'm gonna look for this thing on the slave, I'm not gonna find it. Okay, for you, I'm gonna run that part as well. Okay, see, it's not there, simply not there. So NVIDIA SMI minus L. Oh, it's taking too much time. NVIDIA, oh, I'm on 213, sorry, minus L to log into with 3 dot NVIDIA SMI minus L. Okay, so let's see, like my GPU is being freed up. Okay, so that means like my training is over. Okay, and the training seems to be done. I hope like this video should have give you an essence of like how this distributed training works. I'm gonna create another video, okay, in which I'm gonna cover like the details about the distributed training itself, and yeah, I'll release it in some time. There will like study or look at the different approaches, like how to train your model into a distributed manner. Okay, what kind of distributed trainings are possible, what is model parallelism, what is data parallelism, what is zero, what is federated learning. So all of things we're gonna discuss it out. And thanks a lot for watching. If you're still there, I hope this video is of some use. Thank you and bye bye.